from the Department of Computer Science. The topic she's going to talk about is alternate intelligence. Yeah, as weird as it may sound, it might open up new avenues for us to think. So without any further ado, I'll invite Dr. Damayanti to actually carry on the session.
Thank you, Kapila, for that rather amazing introduction. And it's good to question us up, as always. So, good afternoon, everyone, and welcome here to AP25. This is the first IFA session, and I'm grateful that I'm given the opportunity to talk about alternative intelligence. So, should we take the chat? So, I'm Damayanti Hera, the senior lecturer attached to the Department of Computer Engineering, University of Peradeniya, and I listen about artificial intelligence. I teach some aspects of artificial intelligence. More I read, more I listen about it, more I talk to the people, and more I teach about it, I start seeing an alternative perspective of artificial intelligence. So I thought I will present on that in this session. And I'm very grateful to the IFA organizers for giving me a session, giving me this opportunity to talk about this real topic, alternative intelligence. And I have structured it in such a manner. I'm going to be as much as human possible in this session. So there will be no generated AI generated content on my slides, and there are no texts also, very less text. And I'm just going to be talking for around 1.5 hours or 2 hours about alternative intelligence. So as some people would do, I would make a lot of errors. I would repeat the same thing, redundant things. And so thank you in advance. And so in December, before I go to the session, I wanted to share this feedback link with everyone. So as we go, I think, so I have added a feedback form, and I would be very much grateful if you can share your feedback on the session. We can use the same for the future sessions as well using this Google form. It's bit.ly/IFA session feedback. And last year, in around August 2024, before that, I also have wrote some books today to show. So this book is very famous, The Sapiens book. It's been written by a historian, Yuval Noah Harari. So if you haven't read it, I strongly recommend reading it. It says Sapiens, A Brief History of Humankind. So there are some sequels or subsequent books after that he wrote. He talks a lot about how human came to be where we are today and where will we go, a lot of interesting things. And he is a historian. And but he talks about artificial intelligence as well. And last year, in around August 2024, in social media, I came across this particular video of Yuval Noah Harari, a historian talking about what will be the future of artificial intelligence.
The initials they are, people think it stands for artificial intelligence, but there is nothing artificial about the new forms of AI. They are developing on their own. It's better to think about AI as standing for alien intelligence. I have no doubt, given what we already know, that AI is capable of maybe a different kind of creativity, but precisely because of that, it's really going to be a game changer. So many fields. This is even true of finance. I think about financial devices and the kind of outlook. The first person who came up with the idea of a bond or of a currency or of Bitcoin, this is a lot of fun. It's very creative, very imaginative. So I think you'll see AI creativity also in this field coming up with new types of financial devices that no human being would ever imagine.
It's very interesting. His alternative perspective on artificial intelligence is it's alien intelligence. It's scary to to start with. So is it correct? And also over the time, there have been a lot of creations, movies, books, fictions about artificial intelligence. And one of the most recent ones, very famous, is the movie. The
initial state.
so yeah, this one. Have you watched that movie? The White Robot. So it's an interesting story. You might have already watched it, but if you haven't watched it, it's a beautiful movie to watch with, especially with your kids. Even it can connect very well with kids as well. The White Robot. And this is the trailer of the film. Artificial intelligence and discuss about different. So I start by looking at what are our ancient thoughts around intelligence, how that relate with some of the ancient ideas, how do they relate with artificial intelligence, and there are different ways to achieve artificial intelligence, machine learning, deep learning, being three of them. So I'll briefly discuss and introduce those terms. And of course, we know about large language models like ones behind ChatGPT. So how they came into being and how they work. And I wind up with some notion on the future, what we can expect to happen in the future. So as the subtitle says, it's a very broad introduction to artificial intelligence. So it is not a substitute to what artificial intelligence is, but it's a broad introduction across different topics. All this talking, why I want to do why I'm doing is for all of us to embrace artificial intelligence completely. So I'm trying to provide my perspective what artificial intelligence is, what its different forms are. So especially as educators, we can embrace it comfortably and get to know it comfortably and try to see the alternative perspective of artificial intelligence. Okay, to start with, let's start at the beginning, as always. Start at the beginning. So who are we? Whether we are Hindu or Buddhist, whether we are Asian or American, deep down at the core, we are Homo sapiens. That is who we are. And this is a picture of a Neanderthal man, as they have historians have revealed how a Neanderthal man would have looked like. And as per this book written by Yuval Noah Harari, and he's basically presenting what are the ideas around how Homo sapiens, the us, came to be. So as per him, Neanderthals and we were living together. We were there was in some part of the world there were Neanderthals. There in some part of the world there was Homo sapiens. So how did we overcame? How did we become the prominent species? So there are two theories as per the book. One is we did inbreeding. So we get Homo sapiens, Homo neanderthals, they had babies together, so they did inbreeding, and but somehow the Homo sapiens became prominent. The other theory is the replacement theory, saying that Homo sapiens completely replaced Neanderthals by dominating them, maybe chasing them away. That's the idea. But as this book says, there is a prominent thing about so sapiens. Basically, it's a Latin word meaning one who knows. That is the idea. And as the book says, Homo sapiens are specially, they have one specialty, one special ability is that they can talk about things they have not heard of, things they have not seen, things they have not smelled, but they can still talk about those. So basically imagine this. And it turns out this our storytelling nature has enabled us to connect as communities a lot. So this is where religion comes into the picture. So we had myths, religions, because that could bring together large communities together. It says that when the number of humans are more than 150, this general understanding or talking to each other won't work. We need something beyond that, some myth to believe on, some religion to believe on, so that we can bring large communities. So that's what it says. And it says that maybe in the future, what will happen is we will not change, not only biologically, but our consciousness will also change. I don't know. But so that is the science or stories, histories about sapiens. But what does it mean be human? Rather than me trying to explain what does it mean to be human, I wanted, let's see whether we can feel it. So I would like to listen to this as you listen to this video, watch this video, and try to see what you feel. We have these, and now we have these. So you might be connecting with what I am showing, the tune that is being played in different manners. So there are around 21 people in this room. They will connect in different manners. So now there is something that we can't really explain, something human. You get what I mean? Something human happening there. You are empathizing with that people. This is where, again, maybe a form of alternative intelligence. Can we have artificial intelligence do the same thing? So there has been in the like since a long time ago, there have been a search for what does intelligence mean, and what does truth means? What is the ultimate truth? What is reality? So this is the other book I want to show. So in 380 BC, there is a famous allegory. Allegory means an analogy or like a simile brought forward by Plato. We have heard of Plato, and it is in this book. It's again a very interesting book. And time to time we can get to it and read some philosophical books. So Plato has written this book, Republic. Ultimately, it's a conversation happening with Plato and his teachers. Socrates. They are talking about what is the ideal government should look like, what is the ideal community should be like us. So in this book, there is this famous allegory of the king. This is not really relevant to intelligence, but Plato's allegory of the king try to capture what does truth means, what is truth. But I wanted to show this as an and relate it with some of the ways now we are thinking about what some of the things now we are doing with artificial intelligence. So I try to relate this with some of the concepts in artificial intelligence. So this is how it goes. So as in element of the cave, he discusses about a scenario. In a cave, there are a bunch of prisoners living in a cave. They have been imprisoned in a cave. And they have in front of them is a wall, and they are sitting there looking at that wall. Only thing that, and they are chained. They can't turn their heads, they can't look anywhere else, they can only see what's in their front. That is that is all they can see. And behind them, there are some torch bearers carrying different objects, maybe object looking like a tree, object looking like a sun, object looking like a flower. And there is a fire behind them also, creating shadows of these objects that is being carried by those torch bearers. And all the only thing the prisoners can see is the shadows. And they built up their own reality of the world by looking at those shadows. So they think, okay, and they spell out what this is. So they think that this is love. You can try to relate it with how we are, but how do we think about reality? So they think this is the reality, and so basically the shadows represent not exactly the truth, but some distorted blurred pictures of truth. It's not the truth. And one day it happens that one of the prisoners escapes and he goes out of the cave, and then he sees the sun. He sees the sun. And at first sight, he gets alarmed, so because he's not used to that sun. But later, as time goes on, he gets used to the sun, and now he can see the reality as it is in its clear form. And then he returns back to the cave. And he returns back to the cave and tries to explain this, what he has shown, what he has seen, to his fellow prisoners. And they hit them, as it says. They are because they are not willing to accept what this guy is saying. Okay? So, so as in the library it is said, so basically what they're saying is some bird picture, some representation of the reality, but it's not the reality. So representation learning is something we do in artificial intelligence. So we want to capture a representation of the data we are working with, so that we can do some subsequent tasks. And this very recently in 2024, MIT published this paper, and they are bringing forward a hypothesis called platonic representation hypothesis. So what they say is, if you take the term, what they say is, you can represent, for example, as shown here, the objects, you can have representation in image space. We call them as modalities. So in the image space, we have some representation for what this picture looks like. And we can have a representation, or we can have we can describe the same thing using text. And then, if you look at, let's say you have, for example, for images, you have a vision model to capture these images, and you have a text model to capture the text. If you look at the two representations they have, but in the image domain and the text domain, in these two different modalities, we are same. So somehow they are doing different things, but they kind of have demonstrated that. So the representation here is how does these different models capture the similarity between or dissimilarity between two instances, two samples, and they have shown something. If you try to do it using computer vision or like an image modality, or if you try to do it in a text modality, the representations are same. So they capture something similar. So as it says, a concept like apple and the apple, the real picture of an apple can be viewed in many different ways, but what is represented is not the same. So this, but it still is there as a hypothesis, and they have shown the same with these different large language models and models that we have for computer vision purposes. So that is how they show this theory, this hypothesis, but it is still in exploratory stage. So basically, and in this paper in the other course, so they are talking about what Plato was talking about. Similar to the allegory of the cave. So there is some representation, and we are trying to capture that representation, but it may or may not be the reality. And more than that, what it says is this representation converges, just converges to one thing. Both of them capture the same thing. And okay, so as you can see, the philosophers have been looking at it in different manner. Neuroscientists talk about in different manner. Even this year, we know last year the Nobel Prize for Chemistry and Physics went to computer scientists, and so it means that they are like physicists. We're looking at this intelligence. So after this slide, what I'll be talking about is what we have been doing as in computer science and engineering. So there can be some someone working in cognitive science coming and talking about another alternative form of intelligence. But what I'm going to talk about from here is what we have been doing in artificial intelligence. So mainly I talk about the definition of artificial intelligence and how we try to, what are the branches we are trying to capture and how we try to achieve this. What are the different functionalities we capture? So as I said, so even in history, we have been talking a lot about what is intelligence, how can we make intelligent machines, etc., etc. But especially in the early 19th century or mid 19th century, this was very rigorous. And a lot of work has been done during that period. And I was thinking about it. I think it's very, if you look at it, a lot of things have happened during our lifespan. It's a very, it feels like a long period. But if you take the human civilization, it's a very small thing. And we are experiencing it and we think it's a very big thing. But yeah. So anyway, in 1956, they had this conference called Dartmouth Conference. And there, Professor John McAfee actually wrote a proposal to talk about this topic, what is artificial intelligence. So he brought forward different scientists, people working in the field, and they were trying to work out, they basically had a workshop on this topic. Just maybe I was imagining probably how we have workshops, yeah, to discuss about a recent topic. And so there, they brought forward this definition. So let us define the artificial intelligence as the science and engineering of making intelligent machines. So the definition that stands out, or even it's, I think it's very straightforward to understand about artificial intelligence. It's the science and engineering of making intelligent machines. But before that, in around 1947, this very famous scientist called Alan Turing, famous in computer science and engineering, he wrote a manuscript, interestingly, to the journal Psychology and Philosophy, asking the question, can we build thinking machines? So he basically in this manuscript asked the question, can we build thinking machines? And he also defines what is a thinking machine or an intelligent machine. He says that we have a human doing, we interacting with the human, or we also have a machine interacting with the human. If we can reach a point where this human cannot tell the difference, we would say, okay, we have achieved machine intelligence. So that is what how Alan Turing posed that question. How we can solve this? So he posed this question. So can we build such systems? And the answer is we have. Now we have built that system. So maybe years ago, we have developed systems that can, and they have run tests, experiments, and the audience were unable to distinguish between the basic and profession for certain tasks. And also, one thing I want to highlight is when we talk about artificial intelligence, there are two ways to look at it. One is as developing human-like systems. So oftentimes, when we talk about artificial intelligence, I think we naturally tend to relate it with human intelligence. And somehow we want to compare artificial intelligence with human intelligence. We think about human intelligence. But the definition says nothing about human intelligence. It doesn't have to be human. It should be intelligent. So that intelligence may or may not be human-like. It's something I want to highlight. So why do we think like that? Why do we think that? Why do we try to compare with human intelligence? I think is some people have written about it. Oftentimes, I mean, we think that humans are the more superior. We think they are the best. So we think we are superior more than all the other species in the planet. So we try to compare human intelligence with artificial. That is one thing. The other thing is for us, as we know, human is the most intelligent species. So it makes sense to use human as a benchmark to benchmark artificial intelligence. And so I think there are two ways to look at artificial intelligence. One is making human-like systems. The other thing is self-promotion. What computing did? Computing did in terms of automating things. So we know about industrial revolutions, and now we are in the fourth industrial revolution. And if you look at these revolutions, we have been mainly trying to automate a lot of tasks. And over the past recent years, computing played a significant role in automating things like computer networking, IoT, big data, and machine learning, etc. So it played a unique role in accelerating this work of searching for intelligent machines. But again, when we say intelligent machines, it may or may not be. But to start with, to give you some perspectives about these different branches of artificial intelligence. To start with, we had what I have in the right side. To start with, we try to derive rules. So in artificial intelligence, we talk about entity called agent. So what an agent does is there is an environment, maybe a factory, maybe I don't know, there's some user interacting. So he perceives some percepts through sensors, and then it will derive some action to be done based on some condition, if else rules, or some logics. And then there will be some actuators, how you perform the action. Because there are some motors will be rotated, like that. And again, we interact with the environment. And there can be feedback coming from the environment. We can model a lot of things with this simple model of agent. What is happening? A lot of systems that we are developing. And to start with, in classical AI, we call them as classical AI systems, classical artificial intelligence systems. We did that by deriving rules. So we derived our own rules for that system. And we try to perform tasks. So whereas, so it is like this. In classical programming or in traditional AI, we have rules and we apply those rules on data. This is where how machine learning contrasts with this classical AI system. So what we are doing in current artificial intelligence systems, we don't try to write rules ourselves. What we do is we have the data and we have what maybe the observations we have or the answers we have. Sometimes we call them labels, or we have the dependent variables, whichever that is comfortable to you. And we use especially machine learning to derive the rules. Now, this is like a paradigm shift, a different way to look at it. So rather than we coming up with rules, what we do is we give a large, maybe we give data to the system and let it learn the rules, let it learn the rules. And we can use those rules for different tasks. We can use those rules to do prediction. We can use those rules to do forecasting. We can use those rules to do like identify objects. We can use those rules to predict the next word. We can use those rules to develop chat applications. So that is a key difference between classical artificial intelligence systems and the modern AI systems. And just to complete the picture, I'll not talk about that topic in this talk, but there's another branch of artificial intelligence called reinforcement learning, meaning learning with the feedback. So we get a feedback from the environment and we improve ourselves. And so that is reinforcement learning. And so basically in machine learning, I hope you see the comparison between machine learning and traditional way of problem solving. How we write traditional programs, or how we write traditional systems. But there are different methods to do machine learning, to derive these rules. And one of the prominent techniques, so to start with, we had things like decision trees, support vector machines. So these are machine learning methods. But one of the prominent techniques you are bound to hear that in this term anytime is deep learning, of course. So deep learning is a one particular technique where we do say machine learning using a particular model called artificial neural networks. So it's the interesting thing is it's not a new thing. We started talking about artificial neural networks since in around 1950s. Why? Why the artificial part and why the neural networks? So as I said, we think humans are intelligent and we think the brain plays a huge role in making us intelligent. So it would make sense to mimic the brain if you want to achieve intelligence. So it could make sense to develop artificial systems that can mimic the brain. So this is where, that is why the term neural networks, because in brain, everything happens through neurons and networks of neurons, neural networks, and we are trying to do it artificially, so artificial neural networks. So there can be different forms of artificial neural networks, but I think we all learned about this in our A levels. How does a neuron work? But just to remind us, this is how it works.
Your body and powering neurons communicate with each other, relaying messages throughout your body and powering all of your thoughts and actions. Neurons talk to each other using both electrical and chemical signals. Messages start as electrical signals traveling rapidly down. These signals have action potential.
Signal has a certain weight associated with it. And what we do is we take the sum of weighted inputs and send it through a certain function and we calculate the output. So it is analogous to how, not exactly, but a little bit similar to two neurons being connected to each other, and when a neuron receives inputs, once its action potential goes beyond a certain threshold, it fires. It transfers that in. And if you take a certain task, the neurons that are important to that particular task should be connected. Their weight should be strong. So their connection weight should be strong. This is where, if you have heard, like we talk about a concept called Hebbian learning. So the idea is, as we engage in a task, the neurons relevant to that task, their connections, they get stronger. And the neurons that are not relevant to that task, their connection should weaken. That is one thing. And so anyway, so in a simple model of the bulge, this neuron, we call it as the perceptron model. And what we are doing is, we have bunch of inputs, take the weighted sum of inputs, and send it to a function. And if you can see, I think we all are familiar with simple linear regression. Now we can do simple linear regression with this model. How? So we take the input, multiply it by the weights, take the summation, and we just, our x can be a linear function. It can be a linear regression. And so it turns out, and also we can do a classifier if our f was a threshold function. It's like if our weighted sum is greater than a certain value, we say it's true, or its label is 1, it's a cat, I don't know, like us. So we can use this model to do classification, a simple classification. But it turns out, what we can do with this very simple model, one neuron, is very limited. So then, what we try to do is, without using one neuron, let us use a couple of neurons. Let us not only use a couple of neurons, let us stack them in layers. So basically, we complicate the function. Okay. So by making it an artificial neural network, what we do is, now each of these nodes will have this function and capture some relationship between the inputs. But now, as you can see, it's like we are mimicking a very complex function, and we are mimicking that through these connections and their weights. So this is one form of neural networks, and feed-forward deep neural networks. We call them deep when we have more than 8 rows or layers. We call them deep. And so it makes sense. So it can use as a model to capture very complex relationships. So what do we mean by training a neural network model is deriving these strengths or the weights of these connections. So yeah, but feed-forward neural networks are not the only thing. If you consider this, now as you can see here, at the input layer, we have nodes equal to the number of inputs. And let's say you have this x, it's an image, and you have to learn, it's an x, image of an x. So this is an image recognition problem. And if we have to learn this, so how do we represent an x? How can we use a feed-forward deep neural network to learn x? This has 6 by 6 image. If one can be a pixel, 6 by 6 pixels, 36 inputs. And today we have very large images, very large number of pixels, 128 by 128. So thousands of pixels. So you can imagine if each pixel became an input node in this neural network, we are going to have a large input layer in this neural network. So this is where we talk about convolutional neural network. So basically, what it does is, so I figured I'll do like this today. I don't know how it is. So yeah. So basically, what we're doing is, instead of using the exact input node, let me use a convolution like this, a convolution function. What it does is, it gives me a representation. So one thing with this feed-forward neural network architecture is, every node is an independent network. But if you take, maybe it's not obvious here, but there can be like correlated pixels in this picture, or this x can be slightly rotated. So, but turns out the convolution neural network can capture that, even if it is rotated, and also these four, like this is white, this is white, both of them are white. So they have some similarity. But if you feed it as an independent node, it might not be able to capture it. Whereas we use a function called convolution, and we run them through this image. So we do the first convolution, second convolution, and we take like multiplication with these values. So once I do that, what will happen is, I will have one value corresponding to these 9 squares because I'm using 3 by 3 square. So I am doing a convolution. So that is what is meant by convolution. So I do that and I go here, I do like this. So that is what a convolution neural network does. So it turns out if my function is intelligent enough, it's good enough, I can make that. This is I end up with something like this if I want to do that with this matrix. So basically what I'm doing is the diagonal is 1, right? So if I do this, I will end up with another matrix like this. Now it's compared to this, it's very smaller representation of the same image. I have a smaller representation. And it turns out if I can do it clear enough, this convolution can tell me, okay, these are the edges. Okay, like it can extract out the edges, the horizontal edges, vertical edges in this picture. That makes sense. So convolutional neural network is very different to how a feed-forward neural network works, but it's again an alternative way to achieve intelligence in terms of recognizing images. And so it's a clever idea, and they proposed in 1989. They proposed the very first convolutional neural network. I was coding at that event. So it's very far away. Can you imagine? So we have been talking about convolutional neural networks. It's not that expensive. And this is so Yan Li Kuhn introduced this concept, convolutional neural networks, and this is a recording of how they demonstrated that on a DG. It's very historic moments. This is Yan Li Kuhn. This is very old. There are a bunch of indicators. And he's using that network to detect those indicators. He's demonstrating the convolutional neural network concept. It's recorded in 19. Can you see what we are doing? So we have a bunch of redistributed here, and we are using a convolutional network to recognize what those digits are. And this is like his demonstration of demonstrating that. And but after till around 2010, so even though we introduced this network in 1989, it turns out we couldn't do much due to 2 reasons. One is we didn't have a good data set. We need label data to perform these tasks, and we didn't have good enough benchmark data sets. And the other thing is the computational limitations. In 2010, they launched a project called ImageNet dataset. So what they did was, we had internet at that time, 2010. So they crowdsourced people, they paid people. Fairfield is the one behind this concept. What they thought was, if we could have a good amount of data, we could train a convolutional neural network that can do well on image recognition. So that's the idea. We need large amount of data to train them. Let us gather as much as possible labeled image data. And how they did that was they hired a bunch of people across the internet randomly working hard, like how freelancing now. So they annotated images in the internet or what they have given. They annotated, they labeled this data, and they created this data set called ImageNet. So ImageNet, I want to introduce it because it kind of made a leap, helped in making us a leap in artificial intelligence. And it has around it has a large amount of data and across 44 categories. And so we had a good data set. Now, the other problem we had was we didn't have enough computing power to do this, whatever the training we are doing. But at that time, we started using graphics processing units, or GPUs, to do the computations. And So as we merge these two together, we had a lot of data and we have a good amount of computing power. We saw a boom actually. And they introduced this data set to benchmark image recognition models, basically benchmark convolution neural networks. And in 2012, the AlexNet convolution neural network architecture reached a good accuracy, being able to classify the images in this ImageNet data set with a good accuracy. So we talked about simple machine learning and we talked about image recognition. In terms of intelligence, the other thing very in these days is like very recent time is large language models. So now we know to tackle with some predictive tasks, we can do classification, we can do predictions, and we can also now do image recognition recently better. So we are looking at that. Now there's another thing we want to tackle is the language, natural languages. So in the systems that I have talked about so far, we call them as supervised learning workflow. The idea is I have some annotated or labeled data. So I need to have the data labeled, annotated, and I can use that as the truth. So it's basically like I'm trying to solve an optimization problem. I have my model represented by certain weights and nodes and their dimensions. So my model outputs a value, and then I have the truth value, the truth label, the annotation. Now it's an optimization problem, how to make the model output as close as possible to the truth, the annotation, the label. And a bottleneck we had was manually annotating the data. Something we have looked at a lot because you need a good amount of training data to train a model, label data. And sometimes there are actual practical scenarios we can't have label data. Then came the other paradigm, alternative way to get intelligence, alternative intelligence, using self-supervised learning. So rather than being labeled in tasks, let's just dump a lot of data and let the model extract a representation from that data. I don't know what it means. Some sort of representation, and it doesn't have a label. So these models, we call them as they are doing self-supervised learning. So they don't rely on label data. And such models we also now call them as foundation models, because they can be used as a foundation or a building block to develop a lot of applications. One of those foundation models is transformers. And so transformers, basically what they can do is, given an input text, they can predict what is the next text. It's like, if I give a sentence, on the way to the Kapila invited me to this lecture, on the way to my lecture theatre, I called. So now there's like bunch of text, bunch of words that are candidates to be the next word. And it turns out transformer can do it very well, predict the what is the most suitable word. So the most suitable word would be him. The most suitable would be the couple, because I call the couple. But if you can see, as when I say that sentence, and as something you are doing as an human, so I said, company invited me to the lecture, and on the way to my lecture theatre, I called. So as a human, what you are doing is you are immediately capturing the context of that sentence. You can capture the context of those two sentences, right? Because you relate. That is why you can do the prediction. So transformers were very effective, and like how they made the breakthroughs, they could capture the context. So they, through a mechanism called attention layers, they can capture the text and they can do well this prediction part. But as I said, so the transformer, given an input text, it predicts the most probable next word. In order to do that, it needs an input text. So we call that as the problem. So ChatGPT is based on GPT, which refers to the generative pre-trained transformer model. So ChatGPT was based on transform models, and there have been such generative models for computer vision for images also. What can tools like DALL-E 2, like stable diffusion. So these are again different neural network architectures, different to the feed-forward neural network architecture that I showed. So alternative forms of artificial intelligence, so alternative forms of neural networks. And the other thing, talking about intelligence is, I think, so we talk about prediction, specification, sort of task, and we talk about image recognition, working with images, and the other thing is like a breakthrough that now we can work with language. Language is behind a lot of things we are doing. That is why these GPT models and ChatGPT is like very powerful. It could automate a lot of tasks we do, because deep down, everything we do relates with the language. We do a lot of things with languages. Language is needed for many things. And if you could tackle language part, you do a lot of things. We could automate a lot of things. And the other thing is, when it comes to intelligence, some concept to look at is another alternative intelligence to look at is the memory. So that is another function, in fact, of our brain. So in 2024, as I said, the physics Nobel Prize went to John Hopfield and Jeffrey Hinton. Jeffrey Hinton also, this
year's prize is about machines that the Royal Swedish Academy of Sciences has today decided to award the 2024 Nobel Prize in Physics to John Hopfield, Princeton University, USA, and Jeffrey Hinton, University of Toronto, Canada, for foundational discoveries and inventions that enable machine learning in artificial neural networks.
So it's very interesting. I think everyone was talking about the physics Nobel Prize. So Jeffrey Hinton is a computer scientist. So he went to computer science. So I think it makes sense for me to come and talk at physics executive. Makes a lot of sense now. But there was a lot of buzz at that time. So why are they giving that? But so Jeffrey Hinton is a computer scientist, but John Hopfield, in fact, is a physicist. So he's a physics researcher. And in around 1960s, if I'm not, so certainly if I'm not mistaken, he studied about, he brought forward this idea about memory. Now, before I go there, I would like to take, I was hoping to do like an act. Anyway, so let us take like 1 minute or so. If you can try to memorize one of the most beautiful memories of your life. You can try to memorize one of the most beautiful experiences. And if you can try to memorize, and how do we do memorization? Just forget about thinking. It's about it. We try to just memorize our beautiful experience. So come to think about it, when you try to memorize something, maybe when I ask you to memorize an experience, immediately maybe to your memory might come what I was wearing at that time, where I was standing, what was my background look like. So as you can see, we kind of we don't remember the individual incident as it is, but we kind of have associated relationship with it. Okay, so maybe I was at the bus stop and I was wearing a red frock when I saw him. I don't know. So yeah, so but as you can see, we have some concepts and we have associated these concepts, and that serves as the memory. So this associative memory is something John Hockfield has studied a lot about, and he has brought forward some theories enabling us to mimic memory. That is why this invention is regarded as one of the powerful inventions, probably that what led me to win the Physics Nobel Prize. I wanted to share some insights that he's sharing on winning this Nobel Prize, and I just wanted to share who he is. And
none of his 5 children had taken in physics before naming his 6th child, John Joseph Hopkins.
My parents had a very quantitative view of the world.
But despite the encouragements of his parents, both physicists, the younger Hopfield found his high school physics teacher less than inspiring and gravitated toward chemistry instead. He presented both options to his college advisor, who simply picked up his pen and crossed out chemistry.
And I became this.
That's how it happened.
That's how it happened.
That advisor, a friend of famous physicist John Joseph Hopkins. But physics alone could never contain the younger Hopkins. With a PhD from Cornell, he worked in solid-state physics until 1970, when he unprecedentedly ventured into the biology.
When we look at biology from the point of view of a physicist, biology was miraculous.
After rising to prominence with a groundbreaking theory that shed light upon the infinitely complex physical mechanics of DNA, he became determined to unravel a bigger mystery, the physics behind the human brain.
What fascinates me most is still this question of no mind that comes from a machine.
Hopfield began his research thinking about memory.
Say I have a friend who's tall, energetic, and really loves space. Someone describing that friend could mention just 1 or 2 of these things. Then somehow my brain can fill in the blanks and call up Derek Pitts.
so as it says, if, for example, if I want to recognize this X, and or if I'm given some where the sum of the X are missing, even I might be able to reconstruct that this is an X based on what I have remembered in my memory. So what X looks like. So this is what John Hockfield studied on, wrote theories on associative memory, learning relationships, or remembering a pattern. How can I remember this X? So he introduced the concept of Hockfield networks that can perform this memory. So that was one of the again remarkable inventions when it comes to artificial intelligence. So so there have been different inventions, concepts being brought forward. But also it will be interesting now to think what the future will look like. So what will happen in the future? So I briefly went through some of the concepts, what we have looked at under artificial intelligence. But what will happen in the future? It's my last part of the session. What the future looks like. So this is in 1964, a recording by Arthur C. Clarke talking about the future. It's from the BBC archive.
However, the most intelligent inhabitants of that future world won't be men or monkeys. They'll be machines, the remote descendants of today's computers. Now, the present-day electronic brains are complete morons, but this won't be true in another generation. They will start to think, and eventually they will completely outthink their makers. This is depressing. I don't see why it should be. We superseded the Cro-Magnon and Neanderthal men, and we presume we're improvement. I think we should regard it as a privilege to be stepping stones to higher things. I suspect that organic or biological evolution has about come to its end, and we're now at the beginning of inorganic or mechanical evolution, which will be thousands of times swifter. But even if the future does belong to the robots, our bodies and our brains still have immense untapped potentialities. For example, to cope with the information explosion, we may develop a machine for recording information directly onto the brain. Today, we can record a symphony on tape. So we may one day be able to become instant experts, learning Chinese overnight, for example.
So he talks about we can become in future instant experts speaking Chinese. We are almost there. And like very it's very easy. It's not that hard to work with that very alien foreign language to us. Thanks to translators, thanks to ChatGPT, applications like ChatGPT. So this is how we have been thinking about in 1964 about artificial intelligence, how in the future, how it would be, and have we achieved that? Or I can't answer that question. I'm doing this session for us to answer that question. So talking about the future, so I think I want to introduce this in the future. So in the traditional artificial neural networks, one bottleneck we have is it's very it needs computing power to operate on. And going forward, we are talking about neuromorphic computing with and a different architecture called spiking. Again, an alternative form of neural networks, but not the traditional artificial neural networks that we know, but a different form, a spiky neural networks. So the idea is, if you can see my left side, the input goes to one first layer, it goes to the second layer, it goes to the next layer. It's very sequential. But in spiky neural networks, neurons can spike at any time, anytime. It's not sequential. And turns out this architecture can be very efficient on embedded devices, especially where we have constraints on hardware. So I know Professor Roshan, actually this was taken by one of the students who are Professor Roshan. So I am saying that is that even in Terabyte, there is actually work being done around these things. So neuromorphic computing will be a branch that will be seen in the future, especially trying to incorporate these AI systems into resource constrained hardware, resource constrained systems. And as we go along, anyway, developing these different forms of artificial intelligence, different alternative intelligences, we need a method to benchmark these methods. That is important. So I talked about Alan Turing before, and now there is a series of lecture series that is happening honoring Alan Turing called Turing Awards. So in our field, we highly regard the Turing Award. And in 1960s, I think, Raj Reddy won the Turing Award, and this is the script. It is available online, so you can give all the Turing lectures. And in fact, I checked them. So, right, and it turns out there are a bunch of lectures actually talking about these different forms of artificial intelligence and what will happen in the future. It's very interesting. So how the dialogue has been. So as per him, so his lecture has been titled as, his talk has been titled as To Dream the Possible Dream. And he also talked about different forms of intelligence. He especially talks about what captured my interest is, he talked about an 80-20 rule. So what he's saying is, it's an 80-20 rule. So we are trying to develop systems where artificial intelligence systems, or these intelligence systems, will do 80% of the work, and human will do a 20% of the work. So once we have, dominated, we have achieved an 80%. Now there is a 20% for us to work on. Now we'll go there. And we'll make systems that can work 80% of that. So 80% of that will be handled by some system, but there will be 20% done by the human. We can do another iteration. We can keep going iterations like that. So I want to relate it with benchmarking. So how do we benchmark these methods? How do we evaluate these methods? So in this lecture, he argues, he brings forward that more than knowing what machines can do, it is important to know what they cannot do. So we are struggling to understand what they can do. So there are some funny definitions even, what is intelligence? Whatever that machines can't do is intelligence. So like funny remarks on what is intelligence, how you define intelligence, whatever machines can't do is intelligence. So, so anyway, coming back to the session. So 80 to 20 rule is a like good rule to get it. 80% of the work is done by system, 20% done by human, and we try to repeat it recursively, try to tackle it. And this is one example, one such example. So there is one a benchmarking system for large language models called ArcAGI. Like one instance of benchmarking. How do we do that? So they have developed a benchmark identifying what sort of functions, what sort of tasks, what sort of challenges would be difficult for a machine to handle. That's the idea of benchmark. And in December 20, there was a huge, like in around December 20, they announced, but in December there was some buzz that so GPT-3 model, GPT-4.3 model, the most recent GPT model, could beat this benchmark with a reasonable margin, could achieve a good performance on this benchmark. But does that mean we have reached artificial general intelligence? So artificial general intelligence is where we are heading. We want to achieve artificial general intelligence. So it is what artificial general intelligence means is the systems that can work, mimic humans very well, capturing inputs from different modalities. So they can take images, they can take text data, they can take sounds, and they can process that information and then mimic exactly how humans are working, artificial general intelligence. So, so there was some buzz. So have GPT-3 achieved that artificial general intelligence? The future that we have been talking about is the future is now. So here's Sam Altman, the person behind OpenAI, talking about this.
That people used a lot, and it was this really smart AI that was very far off in the future. As we get closer to it, it's become a less useful term. People use it to mean very different things. Some people use it to mean something that's not that different than O1. And some people use it to mean true super intelligence, something smarter than like all of humanity put together. Trying to use these different levels. We have a 5-level framework. Level 2 with agents now. Start with we can rather than the binary of is it AGI or is it not? I think that became too forced that we get close to life. I will say by the end of next year, end of 2025, I expect we will have systems that can do truly astonishing cognitive tasks like regular users and be like, that thing is smarter than me in a lot of our problems.
I can see the only thing here is that if you want to search, please consider applying to.
I thought that's a great start. 2025. So here's the thing, we will have systems maybe demonstrating more intelligent than as human. Super intelligence. So yeah, but there's one key thing we have to keep in mind, especially as educators, and in talking about these different forms of automated intelligence and talking about AGI, talking about future, it's very important that we have fair, accessible, interpretable, and reproducible AI. This is a key concept repeatedly being mentioned in artificial intelligence. Is fair AI. So, as I said, going back to what Raj Reddy said, so it's about 80 and 20 rule. So how can we know this 80 and 20? So one way to do that would be have fair, accessible, interpretable, and reproducible. So if a model is predicting something, can we interpret why it is predicting so? That is one thing. And there's a lot of discussion just to bring a lot of things into state, bring into the paper. There are some discussions. So basically, GPT-3, they trained them, GPT, they trained that model on large amount of data scraped through the internet. lot of websites. You scrape through a lot of websites. It's like you download the whole internet and use that for training the model. But who puts that data? Who owns that? What is written there? So there is a huge debate around the copyrights of this. And the other thing is, it's also not only a technological thing anymore. There is a political aspect that reading news and all, you will see that there are countries trying to use these technologies to attack other countries. So I think we have to be very much as we comfortably embrace these technologies at the same time, especially for our younger generations, the students who are learning from us, our kids, we have to be aware of these things as well. It's not really something artificial, something is like some magic done by someone, but it's an alternative intelligence that we will have to learn how to live with. So, this is the core of my session today. I wanted to present these different forms of intelligence. That is what I termed as alternative intelligence. Not really an artificial thing. So we can actually see these different forms of artificial intelligence. And so if we look at the past industrial revolutions, this is how we have come so far. So the first revolution came with the steam power, and the second one came with electricity. The third revolution came with the computing, and fourth revolution came from the IoT, big data, cyber physical systems, and the fifth is said to be human AI collaborative systems. So human working very, very, very closely artificial intelligence systems. And again, looking at what this picture explains is how we embraced this alternative intelligence, as I said. To start with, it was just automation. We didn't. It's like we had a factory. We didn't have enough workers. We tried to automate certain tasks. So we developed systems. We had robots. They didn't really have to be intelligent. For example, we programmed them to this point to this point and do a certain thing. But that are very pre-programmed. Doesn't need intelligence because they are working in a constrained environment. Intelligence is needed when there's uncertainty in the environment. No, you can't say a robot working in a factory is intelligent because it's a very constrained environment. It doesn't have any unexpected scenarios to be go where he has to go and do what he has to do. So start with, it was about automation. A lot about automation. Can we automate these things that we are doing? Why? Because as I said, I'm human. Why did we think about that? Because human makes errors. Human get tired. You get tired. We can't do repetitive things. And so we can make errors. So that is why we thought of some alternative way of doing this. And then we took a step forward, assisted intelligence. So we could use this system to assist us make decisions. So we will use that system and make maybe a prediction given by that system, the rules given by that system to do the decision making. The next step is the augmented intelligence. So it is like human and the artificial intelligence systems working very closely to each other. It also involves in decision making. Take chatbot now. It's not really doing any assisted intelligence. It's augmented intelligence. Take a tool like ChatGPT. It's working hand in hand with me, like a companion, and working with maybe some decision making. Very close to the human. But ultimately, what we are looking at is ultimate thing you have would be adaptive system. Autonomous intelligence, where we do not rely on humans. Completely autonomous. It can do its thing. So at the moment, we have human input. So it's like the same thing, 80-20 rule. We can know recursive tackle that it becomes a small fraction. And so with that, I wrap up my talk. I want to show two more books. So this one is a book by Gary Kasparov. So as I said, we have tried to come up with this intelligent machine. And as I said, like in classical AI systems, we were writing rules. And in 19, around 1990s, IBM developed an application called Deep Blue. So Gary Kasparov was a chess champion at that time, world chess champion at that time. And they invited me to play chess with the computer. And it turns out Gary Kasparov was amazed by how computer behaves, how the actions it takes. And at the end, the Deep Blue application has beaten Gary Kasparov. It won all Gary Kasparov. And Gary Kasparov ended up talking, writing, learning a lot about this. So he's not a computer scientist. He was not a computer scientist. But he wrote this book called Deep Thinking. He actually relates how it goes for him to interact with the machine. He talked about his experiences, and then he went ahead and learned about this alternative intelligence and what does it mean. And he winds up his book talking about the future. He says, this is how he winds up his book. He says, machine will give us a lot of freedom. It will give us a lot of freedom, as in it will give us a lot of free time. It will give us a lot of free time. So that we can do other things. So he says, I'm just quoting from this. He says, we can do other things like being creative. And he also says, maybe it's not only about being creative. The main thing is we humans have a purpose. He says we have a purpose. And he concludes his book by saying, maybe if one day humans loses its purpose, maybe it will be like a machine. That is his concluding remarks of the book. And the other book, another interesting book, again, not written by a computer scientist, someone completely out. She's a journalist or she's just a writer, Janet Peterson. She has written about saying 12 bytes, how artificial intelligence will change the way we live and love. So she talks about things like not only dating, I mean, she talks about these different inventions. She talks about sex, how it will change the sexual lives of humans. And how it's been already changed, actually. It's not going to change, it has been changed. So it's a very interesting book talking about how artificial intelligence will change the way we live and love. And this is directly quoted from her book. She says, humans love separation. We like to separate ourselves from other humans, usually in hierarchies. So connectivity is what the computing revolution has offered us. It made us connected. Internet, technology especially, computing enabled us to be connected. But human or machine, we need all the intelligence we can get to wrest the future out of its path with it, whether war or climate breakdown or COVID. Let's not call it artificial intelligence. Perhaps ordinary intelligence is more accurate, and we need alternatives. So with that, I wind up my talk. Thank you so much. Happy days.
There are questions.
I just have a question. I'm from Indian background and even now to start with the question there. Check important what to do related to medicine. This is something I work in ICUs and I see patients who are coming from the neck and struggling to replicate. And I can see patient expressions in the patient, but I don't know what he's saying. So is there a way of detecting the facial expressions
That's a huge database for that image model and so that can integrate what this facial expressions say.
So these are different tasks that you are referring to. So if we are thinking about, because using artificial intelligence, for example, we can do classification tasks, classifying whether he's how his state, a patient's state is, whether he's in pain, he's doing okay. Now it's a classification problem. But large language models come into a picture where, let's say, he doesn't can't directly communicate output text, but there are some other ways we can capture what he's saying or what he's trying to say. So then there's a conversion from one modality to a text modality. So it's like an image to a text or a signal to a text. So this is where we use large language models. So I think the starting point of a problem is the 80-20 rule. So it's like we have to identify what is our traditional methods can do and where actually AI can be helpful. That is what I say, because we don't have to, sometimes people try to use AI for everything. And it might not make sense. And we also have to identify, we have to think how robust that system will be, how critical that is. That is something I didn't touch in this talk, but that's the other thing. So whatever we have done with artificial intelligence so far is whatever we could automate. They are not critical systems. Writing an email, we can have a typo, we can have an error. Writing a report, there can be an error. It's okay, we can deal with it. But we will not use generative AI model to a self-driving car. These systems we call as niche systems. So we have to think of those things as well. If we are like, I think your question is where can we start? Is that correct? So then we need to try to identify where it is difficult for a human to do. Or like you can have some certain of, it's not a quiet place, but you can have some sort of an automation there. If that makes sense, like automate something, some routine tasks, and it can be maybe automated. So you, the doctor can do something else. Like this.
So the video showing live situations using the kind of brain activities using the social media and then they're trying to like interpret on a screen. So I have very sure what I saw when I was reading. So easy to practice and we try.
You can, yeah, it is doable given you have the data. So one thing is, so how we usually start is we try to see whether there are existing work that is being done, maybe a data set that has been already published. And then we can try a model on that data set and see the performance. So it's like already published, so it's like recognized. The next is we have our own data, which may not be as clean as their data. So that is the thing. So there can be a lot of noise in our data. So even if someone says this model works perfectly on this data set, it may not work on our data set. So first we will do a trial of that another data set and see what is the performance. So then we can make some decisions like either we have to improve the model or we have to increase the data size. Or we have to use a different model, likewise. But it's doable. But the thing is, we will not be able to use what is trained on something, some other data, directly onto our data. We will have to do some fine tuning. We call it as a fine tuning. So with that image data set, that is what they did. They trained a neural network that can categorize, classify those 44 categories. And somebody else can take that neural network, the architecture, the weights of that neural network, and fine-tune it a bit. You know, train it on their own data, fine-tune it, and use that. So you are not changing the architecture, you are taking it as it is, but you do some changes to the base. But still, you are using your own data. You need to have your gathered label data. That makes sense. I won't take a model, apply it on some others data, and just straight away apply it for my patients.
For instance, we can do like a big common people, two people, and we show them what they say. So we ask them to take the description of one.
In the department, I think we also have done such research. So, yeah, and it's possible. Sometimes, and the this is some trick or some insight share. When we try to design these experiments, there's a hurdle for us to pass through. That is the ethics review. It's very critical for us to do this. And some organizations allow that if it is already collected data as part of the routine task, you know, the patients are coming to the clinics anyway, and this information is being collected. And if you are certain, if you can guarantee that data is anonymized, you can't say whose data is it. Some institutes are allowing it without going through a rigorous ethical clearance. If you get what I mean, it's like you don't design an experiment from the scratch, from the beginning, but you see whether I can do something with already existing data. Some already gathered data. These are like, it depends on how large your scope is, how much time you have, and how much intervention you can do.
If you mind that there was this very well mentioned, so that single copy would speak all the on the chat, space
But I would see that taken years of research as it doesn't. Like a incredible brains working on it. What I meant to say is like a high research group working on such a system. What I meant by that is who has access to this data very easily and have. So that is like the reality. That is what I say. Of course, you want to develop a system for stable motives. You prioritize them. You get what I mean? So they can prioritize them. But sometimes we can't prioritize them because we don't have that luxuries in that. That is there, that aspect of that as well.
Develop a system for the clinical learn. For example, we examine patients and see the clinical findings. So we can develop a data set of clinical findings as the backup. And whenever there is an example of something coming from, and the students use that as practice. Yes, that is easy.
Yeah, then these kind of applications can be developed using large language models. Yeah. So there are things like intelligent computers, you're doing something like that, right? So what we do is, it's like we use, for example, we can use ChatGPT to do the same thing. But ChatGPT is very general purpose, so it will not know about this clinical data, the nature of them. So we make it more specialized and we develop an application. So there are methods to do that. That would be an LLM based application. Okay, so those were online and here, so I would appreciate any feedback through this meeting. And the main organizer is not here, and I was supposed to do self-service, so I will make a decision.
Yeah, we can. So thank you, Damayanti, and everyone. In fact, I think it's a very humane session where we went through from the start till now. Sit back and think about what's happening. Thank you for the session, and thank you all for joining this online. Thank you. And one more hour.